Here are two more examples of beams with shear and moment diagrams. And this one here has a load that is not symmetrical. It's not centered. So let's see what we should do about that. We'll put the load diagram right under the picture of the beam. And we'll figure out how big are the reactions at each end of the beam. Now, because this load is off-center, we will need to use our old friend, the equilibrium equation, sum of all moments equals 0. And I am going to take moments around point A as my pivot point, so I'll write sum of all moments around A equals 0. Then I'll go force times distance, force times distance. So I have a negative moment, 10k times 6 feet, and I have a positive moment, b times 10 feet. So that gives me, when I smoosh the numbers together, that gives me 0 equals negative 60k foot-pounds plus 10b foot-pounds. And I add 60k to both sides, then I divide both sides by 10, and I find out that b is 6k pounds. I left out some steps here just in the interest of moving ahead fast. So I found b is 6k. Now, how do I find a? I use the other equilibrium equation that's useful here. Sum of all forces in the y direction equals 0. And what have we got? We've got a going up, we've got 10k going down, and we've got 6k going up. That gives us, when you run the numbers together, 0 equals a minus 4k. Adding 4k to both sides, we wind up with a equals 4k. So I added 4k to the reaction at A. Now that we've got those, we'll draw our shear diagram directly under the load diagram. And recall that our shear diagram always starts at 0 and ends at 0. When the load jumps up 4k, the shear goes up 4k. So I can make a vertical line there. Then, between here and the next load, nothing is happening, so we just stay level until we get to that next load. And it's pushing down 10k, or 10,000 pounds, so my shear diagram goes down 10k. I was up at 4k. If I now go down 10k, that takes me down to negative 6k. So now I'm down here. And now nothing is happening until we get to the very end, when the reaction at B goes up 6k. So my shear diagram goes up 6k. And that makes me end at 0. Now we can draw our moment diagram. So we've got our drawing of the beam. Right under that we've got the load diagram, or the free body diagram. Right under that we've got the vertical shear diagram. And right under the vertical shear diagram we'll draw the moment diagram. Again, notice what shape that moment diagram takes. Our shear diagram is horizontal, so that means our moment diagram is going to be sloping. Over here on the end, our shear diagram is horizontal in the negative territory, so that means our moment diagram is going to be sloping with a negative slope. And how do we find the numbers for the moment diagram? Again, the area of the shear diagram tells us the value of the bending moment. So the area of the shear diagram is what? We went up 4k, so we're up 4k pounds, and we have a length of 6 feet. 4k times 6 feet gives us 24k foot-pounds. So I made a slopey line going from 0 all the way up to 24k. Then coming over to the other side of our shear diagram, that side is down in the negative territory. It's down below the 0 line. So over here we have a negative area. Negative 6k times 4 feet gives us negative 24k foot-pounds. So I went from 24k up at the peak. I'm going down negative 24k, and that brings me back to 0. So there's my moment diagram. Here's another example that has two forces, two loads, and they are not symmetrical. Let's look at that. Here's our load diagram under the picture of the beam. And for the next step, we'll figure out how big is the reaction at each end. All right, so because it's not symmetrical, we'll need to use sum of all moments equals 0. I'm taking moments around point A, so I wrote sum of all moments around A equals 0. And what have we got? We've got a negative moment caused by 600 times 2. We've got a negative moment caused by 1,000 times 6. And we've got a positive moment caused by B times 12. So there's our equilibrium equation. And when we boil all those numbers down, we wind up with 0 equals negative 7,200 foot-pounds plus 12b. I'm saving space here, but when I wrote this out on paper, I then added 7,200 to each side. So I had 7,200 equals 12b. Then I divided both sides by 12, and I wound up with 600 equals b. So b is 600 pounds. There it is. Then I'm using another equilibrium equation to find a. Sum of all forces in the y direction equals 0. And what have we got? A going up, 600 coming down, 1,000 coming down, 600 going up. There they are all written in my equation. And that boils down to 0 equals A minus 1,000. I added 1,000 to both sides, and that gave me 1,000 equals A, or A equals 1,000. So there's my reaction at A. Okay, now that we have all our numbers on our load diagram, we can draw our shear diagram. And here we are at the beginning. We start at 0. The load goes up 1,000, so the shear goes up 1,000. Then going along horizontally, then the load goes down 600, so the shear goes down 600. It drops from 1,000 to 400. 1,000 minus 600 is 400. Then it goes along horizontally until it gets to this load. This load goes down 1,000, so our graph drops 1,000 from positive 400 to negative 600. Then goes along horizontally till it gets to the end, and the reaction at B goes up 600, so our graph goes up 600, and that brings us back to 0. Now for a graph like this, you will need to divide your shear areas into separate rectangles, because, let me back up. We have an L-shaped shear graph here. Well, that's not going to work. We need to know, okay, how big is the area in this first chunk? And it is 10,000 pounds times 2 feet. That's 2,000 foot-pounds. So I put a dot on my moment graph, 2,000 foot-pounds. Then the next chunk is 1,600 foot-pounds. It's 400 pounds times 4 feet, that's 1,600. So I added 1,600 on top of 2,000, and that took me up to 3,600 foot-pounds. Then in this last chunk of the graph, we have an area that is negative 600 pounds times 6 feet. That gives us negative 3,600 foot-pounds. So in our moment graph, we'll come from 3,600 down negative 3,600, and that brings us back to 0. Very good. Now, in case you're interested, I did put in a slide here that shows you how you would use equations instead of area to figure out what these moments are. And I'm not going to say anything about it here, but I am going to give you a separate set of PowerPoint slides in case you want to know how people do this. I'll just give it to you without comment, and you're welcome to read through it if you are interested. But as I say, employers do not need us to know how to do this. They just need us to know, here's what the graphs look like, and this is what that beam analysis software is showing us. So let me back up one slide. In this beam example, where we have 2 loads on this simply supported beam, what we found out by drawing our diagram is that the maximum bending moment is going to happen right here at this peak. It's going to be 3,600 foot-pounds, and that is at where? 6 feet over from A. That's the maximum bending moment. That's the thing we're worried about when we're figuring out how big a beam do we need, and do we need any extra reinforcement right there. Last slide, I just wanted to point out that it's interesting to notice that every time the shear diagram crosses the 0 line, that is a point where the moment is at its maximum. Now, in some beams where you've got all kinds of loads going this way and that way, you might have the shear diagram crossing 0 at more than one place, and you might have a moment diagram with more than one peak. But at each point that the shear crosses 0, you will have a peak bending moment. And then what you need to do is just figure out, okay, what is the highest or lowest bending moment? What is the greatest moment value? That's the part of the beam you're worried about.